Today we will be continuing with our work in Chapter 7, estimating parameters and determining sample sizes. We'll be looking at Section 7.3 on estimating a population standard deviation or variance. The process for these are very similar and go very much together on that. We're actually not going to do Section 7.4, so after this section we'll move on to Chapter 8. Okay, this is the study sheet that I have made available to you on Canvas that I've recommended that you print off for your test. So we've covered the confidence intervals for proportions and for mean with the standard deviation of the population unknown, and also the mean for the standard deviation of the population being known. So the last one that we have to do is the variance / standard deviation kind. So with these, you can see that we have a best point estimate of S squared. If you happen to have printed off a copy of this early on, you may see that I had an error here and I've corrected that. So you may want to make that notation, that change here. The best point estimate for the variance is S squared, and actually for the standard deviation is going to be S. We want to identify the values. So in this case, we're going to need our sample size, our sample standard deviation, and then these chi-squared left and right critical values that we'll talk about later in the section. Our requirements, simple random sample for the first one, and it must be normally distributed. There's no flexibility with this. We can't say if n is greater than 30, then we fulfill our requirements. That's not the case. We have to start out with a population that's normally distributed. The way this confidence interval is built, we don't have a margin of error to work with. We simply build it using this format here that we'll talk about. And we have our same interpretation statement. Okay, so like I said, we're just kind of focusing on this one column today. So in this section, we are going to be doing estimates of both the sample standard, both the population standard deviation as well as the population variance. And we're going to use the sample standard deviation and sample variance to do that. So our best point estimate for the sample variance is S squared, and then we'll construct the confidence interval using that. And we'll use what's called a chi-square distribution. So we have our symbol for chi-squared here that you may want to make a note of. So some key things about the chi-square distribution is in a normally distributed population with a variance of sigma squared, if we randomly select independent samples of size n, and then for each sample compute the sample variance, then the sample statistic has a sampling distribution called the chi-square distribution. So we'll be getting our critical values not from the normal distribution, not from the t-distribution, but from this normal distribution called the chi-square distribution. We're going to have what's called a right tail critical value, and we're going to have a left tail critical value that will subscript with a little r and a little l. Everyone will have to get these from the table. We're not going to really be able to get these from technology, so we don't have an inverse t button or an inverse norm button that's going to give us these critical values. So there's different places that you'll have access to the chi-square table, and I'll talk about that in a minute. We will have degrees of freedom with the chi-square distribution like we did with the t-distribution. Our degrees of freedom is still going to be n-1, and so we're talking about a family of distributions and not just a single curve. Okay, so this is what the chi-square distribution looks like. And as you can tell, it is not symmetrical like a normal distribution would be. It's skewed to the right. Another thing to make note of is that all values are non-negative, so it never goes into the negative. So we know that for the t-distribution and the normal distribution, we do have negative values, but for the chi-square distribution, we do not have any negative values. Okay, so as the number of degrees of freedom increases, the chi-square distribution is actually going to get more and more like a normal distribution. So the lower the sample size and the lower the degree of freedom, the more skewed it is. But as the degree of freedom gets larger, the chi-square distribution gets more and more like a normal distribution. Okay, because the chi-square distribution is not symmetric, we're not able to build our confidence interval in the normal way. On all the others, we would take our best point estimate and we would add and subtract the margin of error. We don't have a margin of error because we don't have symmetry in this particular distribution. Therefore, we can't build it in this way. So what we're going to do is we're going to have to use this table A4 to find our critical values and then develop our confidence interval from that. Okay, so this is a copy of the chi-square distribution, and I know the quality of it is not great. What I would suggest doing is one of a couple of things. One is if you go to page 687 on the e-text in MyStatLab, then you'll have access to the table there, and you can print off a copy if you need to. The other is that in MyStatLab, generally on a problem, it gives you the option to click on the table that you're going to be using. So when you click on that table, then you're going to have access to the distribution. I have uploaded a copy on Canvas that under the Chapter 7 material, and that may be a little bit clearer if you want to print that copy off. Okay, and so this kind of summarizes where you can where you can come up with those copies of the table. Okay, so how do we use the table? We're going to work with finding the critical values of the chi-square distribution. So we're given a simple random sample of 22, so this is our N, 22 IQ scores. Okay, we want to construct a confidence interval for the population standard deviation S that requires the left and right critical values of chi-squared corresponding to a confidence level of 95%, a sample size of 22. So the main two things that we need to think about right now in getting our critical values are the confidence level and the sample size. So what I'm going to do is I'm going to sketch this out. I'm going to draw my distribution that's somewhat skewed. We know it starts here at 0. So what we're going to do is, just like we did before when we put 95% in the middle of our graph, we're going to do that again. And it doesn't really matter that it's centered up. What matters is that we have half of the area here and half of the area here. So if we take our 0.05 and divide that in half, we'll have 0.025, and that's the part that we need to make sure is in each tail of our graph. Okay, so we'll take the 95, put it in the middle, split the remaining part. This is going to be chi-squared left, and this is going to be chi-squared right that we've got defined. So what we're going to do is on our table, if we look over here at this table, you can see that it says area to the right of the critical value. So just keep in mind that that's what you're going to see up here. So in every other case, when we did inverse norm and inverse t, we use the area to the left. But for this table, we're going to use the area to the right. So if we look at this, if I'm trying to find chi-squared left, that's this value here, then I'm going to need to know the combined area to the right. So what I'm going to do is I'm going to use .95 plus 0.025. So I'm actually going to use 0.975, and my degree of freedom is going to be n minus 1, so it's going to be 21. So when I go to my table, I'm going to go up here to where it says the area to the right is 0.975, and then I'm going to go down to the number of degrees of freedom, and so this is going to be my value here that I'm going to use. So 10.283. Okay, so 10.283. But if we go back and look here, if I'm going to find chi-squared right, I'm going to be using, I'm going to look here, and my area to the right is 0.025, and so I'm going to have 21 degrees of freedom for that one as well. So on my table, I'm going to go to 0.025 and then 21 degrees of freedom, and so that's my other value that I'm going to be using. That's my chi-squared right. So I'm going to have 35.479 for my chi-squared right, and then I'm going to have 10.283 for my chi-squared left. Okay, here's one I'd like for you to practice with. I want you to find chi-squared right and chi-squared left for a 90% confidence interval, and we want to do this when n equals 25. Okay, on this one, we want to draw out our chi-square distribution, and we're going to put the 90% in the middle. So we'll put 0.90. That leaves me with 0.10, excuse me, because if I've got 90%, then I have a 10%. So 0.10 divided by 2 gives me 0.05. So that's the part that goes in each tail. This will be chi-squared left. This will be chi-squared right. So for chi-squared right, I'm going to use 0.05 and 24 degrees of freedom. And for chi-squared left, I'm going to use 0.95 and 24 degrees of freedom. So looking at my table, when I do that, using 24 degrees of freedom, and we said we're going to use 0.95 for chi-squared left, and then I'm going to use 0.05 for chi-squared right. And so those are my two values that I'm going to see as my chi-squared left and chi-squared right. Okay, so we want to put this all together and actually construct an entire confidence interval estimate for this. So a few symbols that you need to make sure you're familiar with. You've got sigma, which is the population standard deviation. Sigma squared is the population variance. S is the sample standard deviation, and S squared is the sample variance. N, of course, is your sample size. E would be your margin of error, which we're really not going to be finding a margin of error for these. And then we've got chi-squared left and chi-squared right. This should be right-tailed. Okay, so for our requirement check for this, we need to know that it's a simple random sample, and we also need to know that the population is normally distributed. So we don't have to do the n greater than 30 or any of that. We just need to know it's normally distributed. Okay, so this is the formula for our confidence interval. We're going to substitute in for the n, which is the sample size. We're going to substitute in for the s, which is the sample standard deviation, or actually S squared would be the sample variance if you want to look at it that way. Then we're going to have our critical value, which is chi-squared right, and then we're going to come over here and do the same thing on this side except put in chi-squared left. So we won't substitute for here in the middle. We'll leave the variance here in the middle for the population variance. So this is the one that we're going to use for estimating population variance. Okay, if we want population standard deviation, that we know that to go from variance to standard deviation, we simply take the square root. And that's what we're going to do here. We're going to take the square root of everything. So the square root of sigma squared is just sigma, and we'll take the square root of this side as well. Okay, a couple rules on rounding just to remind you. If we have the original data set, then we want to go one more decimal place than is used for the original data. So if my original data showed 1 decimal place, then I'm going to round to 2 decimal places. So I'm going to go one more decimal place. If I'm given summary statistics, so in other words, I'm already told what my standard deviation is, then I'm going to round that to the same number of decimal places as the standard deviation. So my endpoints are going to be rounded to the same number of decimal places as the standard deviation. Okay, so our procedures, we'll verify the requirements, we'll find our critical values, we'll get our confidence interval estimate for the variance. If we need to, we'll do the standard deviation by taking the square root, and then we'll make sure that we've rounded. Okay, in this problem, we are going to be working with some summary data for 22 full IQ scores for a group of people that had medium exposure to lead. And we're told that we have a standard deviation in that group of 14.29263. We want to consider the sample to be a simple random sample and construct a 95% confidence interval of the standard deviation. Okay, so looking at this, we have a few things that's known. We know that our sample size is 22. We know that our sample standard deviation is 14.29263. If you notice, they're giving quite a few decimal places here, and you really need to, even if you had the original data set and you put that in L1 and get your one variable stats and find your standard deviation, you need to show it to several decimal places here. And we want to find the 95% confidence interval of the population standard deviation. So we're basically going to be using this formula Okay, one thing I want you to make note of in the formula that I didn't mention earlier is that the right goes to the left and the left goes to the right when we apply it to this formula. So it's not that way when we're looking at the critical values, but once we go to the formula, they do switch. So on this one, the first thing we're going to do is we're going to look at our requirements, because if they're not being fulfilled, there's no point in doing any of the rest of the work. So simple random sample, we're actually told that here. So we're good with that. We're not told that it's normally distributed. So what we can do is if we happen to have the data set, which in this case we don't, but if we were to have the data set, then we could look at the histogram, we could look at our normal quantile plots and make a decision from that. So this does appear to be approximately normally distributed. So we're going to go ahead and assume that it's normally distributed. Okay, the next thing we want to do is to find our critical values. Okay, so with our critical values, we are going to look at our chi-square distribution. This one was for 95%. So we'll have 0.025 in each tail. So it'll be chi-squared left and chi-squared right. So this is actually one that we found earlier. And so if we look at this, for n equals 22, we would go to a degree of freedom of 21. And then for 95%, we're going to look at 0.025 as the area to the right of the chi-squared right. And then this was 0.95. So the area to the right of this one would be 0.95 plus 0.025. So we'll use 0.975 and 21 degrees of freedom. And we'll get these two values here as our two critical values. Okay, so from here, we're ready to set this up. We found our two critical values and we figured out what our, we were given all of our other information. So when we go to plug this in, we're going to put in chi-squared right here. We're going to put in chi-squared left over here. And we know that if we divide by a larger number, then that total is going to be smaller. And that's why we divide on the left side by chi-squared right, and we divide on the right side by chi-squared left. So you're plugging in the n, you're plugging in the s, and you're putting in your chi-squareds. Simplify each of these expressions here, and when you get those simplified, you're going to end up with 120.9 and 417.2. This would be for the variance. Okay, but this particular problem asks for standard deviation. Some may ask for one or the other, and some may ask for both. This one was asking for standard deviation. So what we want to do is we want to go back. Don't take the square root of the 120.9. Take the square root of the 120.9127856. Take that square root. That's going to give you the value you need for your standard deviation. If you take the square root here, you're going to get an error introduced into that. So this would be my standard deviation. Okay, so we would say we are 95% confident that the interval from 11 to 20.4 actually does contain the true value of the population standard deviation of IQ scores for medium lead exposure. Okay, and so if you want to read through these are kind of the book's explanation of this particular problem. You can see it's going to pretty much take you to the same place that we ended up. One thing to point out is because we don't have that symmetry, we can't just simply take our S and add and subtract some margin of error to it. Okay, so we can't really format it in that form. So you do need to write it either as this with the sigma between it or the parentheses with the comma, but we can't use this format for the confidence interval. Okay, here's one that I would like for you to try. So pause the video, try this one, and then check your work. Okay, we see that we have a sample size of 20 cigarettes and we have a standard deviation of 1.6. Now on this one, they don't tell us which standard deviation it is. So technically it could be sigma or it could be S. But because the standard deviation is coming from the group of 20 cigarettes, if it's coming from a sample, it's going to be an S and it's not going to be a sigma. So we're going to get rid of that part here. And we know that our sample size is 20, as we said. and we know it's normally distributed. So if we start looking at our requirements, we said we're just going to make the assumption it's a simple random sample, and we're told that it's normally distributed. So we're pretty much ready to go with this. When I go and find my critical values, this one we said was 95%. So it looks very much like the sketch of the previous one, with the exception being we have a different degree of freedom. So our sample size is 20. That means my degree of freedom is one less than that, or 19. So when I go to my table, I'm going to use 19 degrees of freedom, and for chi-squared right, I'm going to use 0.025, and for chi-squared left, I'm going to use 0.975, because the table calls for the area to the right. So the right of this line would be 0.025. To the right of this line, we'll add these two together and get 0.975. Okay, so here we're going to have n minus 1, which is 19 degrees of freedom. And we said that we're going to use 0.025 for my chi-squared right. And for chi-squared left, I'm going to use 0.975. So when I come down here, I'm going to have 8.907 and 32.852 for those two values. What I'm going to have is I'm going to have n minus 1 s squared over chi-squared right. And then I'm going to have n minus 1 s squared over chi-squared left. So that's going to be 20 minus 1. My s on this one, we were told was 1.6. Chi-squared right, we just got through saying was 32.852. We're always going to put the larger one on this left side. And then here we're going to have 20 minus 1, and we're going to have 1.6 squared. So our numerators are going to be the same. And then here we're going to have the 8.907. Okay, when we simplify this, we're going to get 1.480579. And here we're going to have 5.46087347. And I'm doing this to several decimal places because I already know that I'm going to need to find the variance and standard deviation on this one. So because of that, I'm going to look at this where it has all the decimal places shown. So when I do this, I can see that 1.5 and 5.5 are going to be the endpoints for my variance. And then for the standard deviation, I'm going to actually take the square root of those numbers. So it's good to kind of hang on to them throughout the problem. Okay, so when I take the square root here, I'm going to get 1.2. And then on this one, I'm going to get 2.3 as my answers. So we would say we are 95% confident that the interval from 1.5 milligrams to 5.5 milligrams actually does contain the true value of the population variance of nicotine content in cigarettes. And you could do a similar statement for standard deviation as well. Okay, here's an example where we start with a data set. So I'd like to give you a minute to try this one, and then we will see how what you should have done with it. Okay, when we look at this problem, we're asked to find the 90% confidence interval for both the variance and also the standard deviation. Okay, so we're going to find two in this one. Assume it's normally distributed for our population, and then here we have this data set. So when you start with a data set, what we want to do is we want to go to L1 and enter our data. Okay, so I'm going to give you a minute to pause the video and go in and enter this data. Okay, once you have it entered, you're going to go to one variable stats, and you're going to find the S sub x, and that's going to be 5.312459. said before, write that to several decimal places so that you maintain your level of accuracy. All right, this one, we've got to check our requirements. So we've got a simple random sample and normally distributed. We're told it's normally distributed, so we're good with that. So we're ready to find our critical values. So this one is a 90%. So I'm going to take 90 and do 1 minus 90, which will give me 0.10, and then divide that will be 0.05, and that's what's going to go in each tail. So this is going to be chi-squared left and chi-squared right. Okay, so to find chi-squared left, I'm going to use everything to the right of that, which will be, I'm going to use 0.95. And for chi-squared right, I'm going to use 0.05. And that's with, for my degree of freedom, if I count these, what I'm going to see is that I have 10 values, so my degree of freedom is 9. So I'm ready to get these critical values here. If I look at my chart here, I have a degree of freedom of 9, and we said that we're going to use 0.05 and 0.95, so here and here. So we're going to use 3.325 and 16.919. Okay, so those are the two critical values that we'll be using. So we're ready to go ahead and put this all together. We'll have n minus 1 s squared over chi-squared right and n minus 1 s squared over chi-squared left. Okay, so my n was 10, we said, so we're going to have 10 minus 1. Our s is 5.312459. We'll square that. Our chi-squared right value that we got from the chart was 16.919. I'm just recopying this numerator here. And then I'll divide that by chi-squared left. And my chi-squared left value is 3.325, again, coming from that chart. So when I simplify all of this, I'm going to get 15.012706. And here I'm going to get 76.39097312. Okay, so once I get to this point, I'm pretty much ready to go ahead and write my answer. So for the variance interval, I just need to round this appropriately. So these are whole numbers, so I want to go 1 decimal place more than that. So I'm going to have 15.0, and I'm going to have 76.4. Okay, for the standard deviation, I need to take the square root of these. So if I take the square root of 15.012706, I'm going to get 3.9. And then if I take the square root of this number, I'm going to get 8.7. Okay. So be sure that you maintain your level of accuracy by carrying your decimals forward in the problem, and take the square root to get your standard deviation. When you're writing the interval for variance, you should have sigma squared here in the middle. When you're writing the interval for standard deviation, then you should just have sigma in the middle. Okay, and so that takes us to the end of this section. This is kind of the summary of all the different types of confidence intervals. So I wanted to do one more thing to kind of pull all the confidence intervals together, and that was to put kind of look at them in terms of using the calculator, and also when they're all mixed together, being able to tell the difference between the two. So if I look at these, we already knew that proportions, you go to 1 proportion z interval, not test, interval. For the mean with sigma unknown, you go to your t intervals. For mean with sigma known, you're going to go to your z intervals. And there is no calculator function available for standard deviation and variance. So we're not really able to use a calculator on these. There are ways to do them. You can find apps online where you can download onto your calculator that will do them. There's just nothing preset built into your calculator. So, and the table A4 is pretty easy, so I don't really see the need in doing that. Okay, I've put 5 different problems here. We're not going to do these 5. What I want you to simply do is to read the problem and identify whether it is a proportion type, mean with sigma known, mean with sigma unknown, standard deviation, or variance. So I want you to read all 5 and label them appropriately as to the type, because I think a lot of times people know how to do them as long as they know the type, but figuring out the type is the hard part. So take a minute, read through them, and then check your answers. Okay, on the first one, I've always said go to your construct statement. So here's my construct statement. It's telling me what I'm going to be building, and I'm going to construct or build the 90% confidence interval of the mean. Okay, so with mean, I need to know is sigma known or is sigma unknown. So when I look at my standard deviation here, which is what sigma is standard deviation, I do have a standard deviation given, but it's referencing this sample, okay? So if it references the sample, then it is not sigma, it's an S, and therefore this one would be a mean with sigma unknown. Okay, number 2, construct a 99% confidence interval estimate of the population standard deviation. Here's my construct statement, and what I'm constructing is a confidence interval of the standard deviation. So this is going to be a standard deviation type, just like we looked at today. So a lot of people think, okay, this one has the word standard deviation, and this one has the word standard deviation. Yes, they both do have the word standard deviation, but they're very different in terms of how you approach the problem. It has to do with what you're constructing, not what's given in the problem as much as what you're asked to construct. Okay. All right, number 3, there's the find or construct statement. So find the 95% confidence interval for the population proportion. So this is going to be a proportion type. Okay, the next one, here's my construct statement. Construct a 95% confidence interval estimate of the mean. So this is going to be a mean type. And I'll look back and it says the population standard deviation is 0.54. So population standard deviation is sigma. So this would be a sigma known. Remember, if sigma is unknown, then you use a T critical value. And if sigma is known, you use a Z critical value. And then the last one, we're going to construct a 90% confidence interval estimate of the variance. So this is going to be a variance type problem. So it's going to be done with the chi-square distribution. So numbers 2 and 5 would be done using the techniques that we learned today. 1, 3, and 4 would be done using techniques that you were tested on already. So that's kind of showing you the difference between the different types of confidence intervals. Okay, so that concludes today's lesson and also the Chapter 7 material on confidence intervals. As always, if you're having questions, please take advantage of the resources, whether it's attending SI sessions, office hours, getting a tutor through the ARC, or just emailing me a question. All of that's very helpful and hopefully can get your questions answered. Thank you and hope you have a good day.